Astrobot.
Hi everyone! Welcome to these video lessons about space engineering. The idea is to provide intuitive explanations as well as the mathematical steps to develop the topics. The first lesson will cover the backbone of rocket science, the rocket equation. This equation was called after Konstantin Tsiolkovsky, who was a pioneer in this field. Since then, it became a tool of fundamental importance in space engineering. First of all, let's try to understand the origin of thrust. Consider a rocket completely filled with propellant at the initial time t0. The overall mass of the system is m. The initial velocity is a vector called v. Obviously, if the rocket is initially static, v is equal to 0. After an infinitesimal time interval dt, the rocket has lost a small fraction of the initial propellant. Its mass is equal to the initial mass m minus the infinitesimal mass dm, which represents the amount of propellant lost in dt. Moreover, the rocket has been accelerated to the velocity v plus dv. Now let's move to the exhaust. Its infinitesimal mass is dm, exactly the same mass lost by the rocket. Its velocity is equal to the initial velocity of the rocket, v, plus some unknown velocity u. Keep in mind that in real rockets, u can be in the order of some kilometers per second. The third law of dynamics, developed by Isaac Newton, requires the rocket and the exhaust to move along the same line, but in opposite directions. This is the reason why we have to expel propellant from the rear in order to move forward. Now it's time to write two equations, the conservation of mass and the conservation of momentum. Since both mass and momentum are conserved for the overall system, we can equate mass and momentum at time t0 and mass and momentum at time t0 plus dt. The overall mass of the system at time t0 is m. The overall momentum of the system at time t0 is mv. The overall mass of the system at time t0 plus dt is m minus dm plus vm. This is the result of the summation of the rocket and the exhaust. The overall momentum of the system at time t0 plus dt is this more complex expression. Again, this results from both the rocket and the exhaust. Let's equate left and the right hand terms. This is the conservation of mass. As we can see, it's trivial, being nothing more than an identity. The momentum equation instead is a lot more meaningful. This is what we obtain after extracting all the terms in brackets. We can subtract this term from both sides. The same is true for these other terms. We can then neglect the term dm dv being an infinitesimal of higher order, definitely a tiny quantity. What remains are just two terms. If we divide both sides by the infinitesimal time interval dt, we obtain the final form of the momentum equation. By exploiting the second law of dynamics, we can see that the left-hand term is actually the thrust. We have discovered the dependence of the thrust on the exhaust mass flow rate and the exhaust velocity. It's time to move to the rocket equation. The assumption is that the thrust is the only force acting on the rocket. No gravitational attraction, no aerodynamic forces, just thrust. This is quite accurate when traveling in deep space. It's pretty inaccurate when traveling in the atmosphere of a planet, but still a valuable tool for preliminary computations. All that said, this basic equation is our starting point. If we write the instantaneous mass at time t as the initial mass m minus m dot t, where m dot is the propellant mass flow rate, and if we remember that acceleration is the time derivative of velocity, we can rewrite the equation in this way. Up to this point we had a vector equation in the 3D space. From now on we will move to a 1D scalar equation, since we are not interested in directions, but just in magnitude. By rearranging the terms, this integration in time provides the delta v, that is, the variation of velocity felt by the rocket during the burning. This quantity is of great importance, since orbital maneuvers always ask rockets to provide a certain delta v's for their correct actuation. The higher the delta V, the larger the amount of propellant required. Going on with the integration and assuming both thrust and mass flow rate constant, we find the logarithmic behavior of the Tsiolkovsky equation. We can exploit the properties of logarithms to rearrange terms. To close the lesson, a final definition is required: the specific impulse. The specific impulse is equal to the impulse, that is, thrust multiplied by the time interval during which thrust is applied, divided by the weight of the propellant expelled during this time. G0 here is the acceleration of gravity at sea level. The result is this compact equation, which describes the meaning of the specific impulse, the ratio between the thrust provided by the rocket and the rate at which propellant has to be expelled in order to grant that thrust. In other words, the specific impulse gives the efficiency of the rocket in terms of how much propellant I am asked to spend if I want that specific thrust. All that said, the final form of the Tsiolkovsky equation is this one. Mr stands for mass ratio, and it's equal to what we saw in the previous steps. Again, this equation assumes thrust as the only force acting on the rocket. Moreover, mass flow rate and thrust are assumed constant. Consequently, the specific impulse as well is constant. In real life, none of these hypotheses is correct. Moreover, this version of the Tsiolkovsky equation considers a single stage. We will discuss improvements of this equation in future videos, so stay tuned. One last thing. As you can see, thrust does not appear in this equation. This means that the same delta V can be given by both a super high thrust solid rocket booster and a very low thrust ion engine. What changes is the time needed to provide this delta V. A very long time for the ion engine, a very short time for the solid rocket. Thank you.